Okay, good afternoon, everyone. I'm Yueming, a scientist from CFA. Today, my talk is black box optimization for diffusion model target generation. Okay, first, what is black box optimization? Given a proper function such that it is lower bounded, we aim at minimize the fx using the function queries only. It means we don't have the gradient. We only have the function value fx. Okay, why we need black box optimization? Because many real-world applications we cannot access the exact gradient. For example, from fine-tuning for vision and language models, we can only access the API calls. Also, for 3D molecular design for drug discovery tasks, we can only access the simulation package feedback score, like the VINA docking score, to compute the molecular, the VINA docking connect energy for the molecular connect to the target protein. Also, for new material designs, we can only access the expert preference feedbacks. Usually, it is black box. Okay, how to perform black box optimization? Black box optimization has been investigated from different communities for several decades. For example, evolutionary algorithm and genetic algorithm has been studied in the evolutionary computation communities. Usually, these kind of methods are heuristics. The convergence is very slow. In machine learning community, we focus on zeroth order optimization or distribution sampling-based black box optimization. Also, we are interested in Bayesian optimization. This kind of algorithm usually build a surrogate using the Gaussian process and analysis the regret bound for different functions belongs to different RKH family. Another kind of black box optimization is a direct search. Usually builds a search on the grid or on the lattice. The last one is a deep learning model based. Usually it train a deep model use the offline data. Okay, today I will focus on sampling based black box optimization. When we want to optimize a black box function fx, we relax the problem as the expectation under some parametric distribution P. So the new problem becomes the J theta. Now we optimize the parameter theta with respect to the distribution, not the fx itself. Okay. When we use the Gaussian distribution as the sampling distributions, this problem can be simplified. We add a KL divergence regularization using the first order Taylor expansion, and we can achieve a closed form update for the covariance metric term and mean vector term for the Gaussian distribution. In this update, we only involve the expectation of fx. There's no gradient nabla fx. So when we use the Monte Carlo sampling to approximate this expectation, we can take the update. Okay, here is the algorithm. At each loop, we take samples using the current Gaussian distribution and the queried function values for different for the batch size for different x. Then we get the function feedback. We use this function value feedback to update our parameter covariance term and the mean value term. Okay, now we can plug in our algorithm to the diffusion model to perform target diffusion model target generation. In diffusion models, we have forward SDE and backward SDE. For pre-trained diffusion models, we have a fixed score functions approximate using the neural network. Now we add new parameters of the drift term mu and the covariance term sigma. So in this framework, we start from Gaussian noise, use the pre-trained pre-trained diffusion backward SDE to take samples, to take a batch of samples like different cars, and evaluate the score of different samples based on some simulation package, and use this function value feedback to update the mu and the covariance. Okay, so when we discrete time, we can perform a finite time update. So it has a fixed drift term of the pre-trained model and now a parametric distribution Gaussian noise. So we want to minimize the cumulative target scores under a sequential Gaussian distribution. Note that at each step, the value xk depends on all the sampling trajectory. Okay, similarly, we add a KL divergence regularization. We can derive the update for the mu term and covariance term, and use this term to take the sampling in the loop. Here is the algorithm. Each time we take samples from Gaussian distribution, and each time and each inference step, we take Gaussian distribution. Take samples from Gaussian distribution and query the black box target score for these bad samples, and loop this procedure and update the mu and the covariance term. Now we want to analyze some theoretical properties for a sequential optimization problem. The summation of the sequential small fx. Here, the sk bar depends on the previous trajectory s1 to blah blah xk. This optimization problem is quite interesting because it involves some interesting examples. For example, the sequential update under some unknown transition dynamics. Okay, we relax this problem under a sequential Gaussian distribution. So here's the algorithm. In this algorithm, we use some regularization to control the eigenvalue of the our covariance matrix. This technique is used to derive the convergence rate. Here is an assumption of the we used. So for the sequential problems are all convex functions and they are Lipschitz continuous functions. The third assumption is the value is bounded. So under these three assumptions, our algorithm can achieve a sublinear convergence rate, the capital O over 1 over square root T. Here in our experiments, we perform the target image generation and target 3D car generation. For the image generation task, we use the Gemini as the evaluation metric to compute the score. We use the pre-trained the text-to-image model, the stable diffusion model 3.5. For the target 3D car generation, we use the drag coefficient as the objective. Also, we use the drag force plus lift force as the objective. We use the pre-trained text-to-3D model. Okay, here's the baselines. The first one is the flow GRPO. The next one is the DNO is usually optimize the noise sequence. The third one and the fourth one are the inference time alignment method in this year. Okay, for the image task, we compute the Gemini rating scores over different prompt tasks. The purple line is our method. We can see our method increase the score very fast compared with the baselines. Here is the average Gemini scores compared with the baselines. The larger is better. The first one is our method. It is larger than the baselines. Here is some demonstration of the generated image. Here's the pre-trained image. The target prompt is a natural fluffy dog talking to a cybernetic dog. Here is the generated results of our black box guidance. Here is another example. The target prompt is a cat with fluffy with butterfly wings. Here is the results after our black box optimization. Okay, now we test our algorithm on the 3D car generation task. We use the drag coefficient as the black box scores. Here is the comparison with baselines. The first one is ours. Our method can achieve a smaller drag coefficient, also a smaller drag force plus lift force compared with baselines. Here is the optimization trajectory compared with baselines. The purple line is our method. We can see our method decrease the score faster compared with baselines. Okay, here is a demo video of our generation for the 3D car. The target is minimize the drag coefficient. As the optimized iterative update, the car shape changed. Okay, here's some work for our black box optimization. Okay, thank you. Any questions?
So thank you very much for the great talk. So I'm not quite familiar with this topic, but can you somehow combine like differentiable simulation idea in this kind of like design issue?
Yeah, basically we use the black box optimization to get the pre-trained diffusion model to generate our target.
Yeah, but can you take the gradient information, for example, not only a point, but can you also utilize gradient information?
Gradient, but for example, for the car generation task, the value, the score value is a black box. We can use a simulation package to compute the score. We cannot access the gradient.
Can you learn the simulator in a differentiable
you mean learn
way?
the simulator? Usually, you need a lot of samples and to pre-train a surrogate, but when you generate samples and compute scores, it takes quite a long time. For our method, even we use this online generation, it takes 8 hours for 200 iteration.
I see. Thank you very much.
Yeah.
So thank you very much for your talk. Sorry, I a little bit missed your method. So okay, so you use like a diffusion model to sample some data point. So then it looks like you use like the sample of internal steps of diffusion model. Am I right? Are you using?
Yes.
Okay, like a steps is a k equal 0 to something. Yeah. So then is it better to use the intermediate solution, or just using the final sample is not enough? I mean,
you mean the internal samples or the generated samples at the last step?
Yeah. So maybe you evaluate the function value also.
Yes.
For the
in our method, we evaluate the final the final step X and build a Gaussian process to evaluate the internal samples to compute the internal scores.
Yeah. You use internal steps to.
Yes.
Okay,
I think this can be viewed as a regularization for the whole trajectory instead of the final one.
I see. So you have a kind of multiple resolutions, so then it's better to use the internal steps instead of using just a final solution. Okay. So okay, I understand. Thank you.
Okay, thanks.
Any other questions? Okay, so one question. So how about the dependence on dimensionality? So usually black box optimization suffers from high dimensionality. So do you have any comments?
Oh, okay, sure. I think for this kind of problem, when we use the sampling from a Gaussian distributions, it can be scale up to high dimensional because it's a unimode. Maybe it can track to some local optimal, but it is scale to high dimensional compared with other methods like Bayesian optimization and for other global optimization techniques.
Okay, okay. Yeah, thank you. Okay, so any other comment? Oh,
how much have you found the covariance to help in practice? So you're doing this extra work to learn the sigma.
Yes.
How much does it help?
Because the sigma controls the scales, and I think in our experiments we found it can help to accelerate the convergence, especially because each sampling step the scale is different. Use this learned scale can help. For the standard Gaussian distributions, you usually use an isotropic Gaussian distribution. It cannot scale to handle the air condition problem or the problem with different scales. This idea is similar to the ADAM. It can work well for the deep learning models.
But I imagine it's not so easy to learn it well if you only have access to the function values, because the sigma is related to the second derivative, maybe of your,
yes.
And then you're trying to estimate the second derivative just through function evaluation. And I feel that might be difficult to scale to high dimensions. Have you found some difficulties with this, or?
Oh yeah, in our work we use the diagonal matrix. I think it can be used as regularizations. The diagonal covariance matrix is computation fast. It does not involve to take the high cost inverse, the metric inverse. So yeah, and this regularization can also help to learn the diagonal values faster compared with your learn a full covariance matrix. I think, yes, this may be also observed in the optimizer like the ADAM or the ADAM-W. They use the diagonal covariance, a diagonal scale from preconditional matrix.
Okay, thank you.
Other comments? No? Oh, about 10 minutes remains, so it's great. So.
Okay, I can show additional some demos of our work.
Please show us.
Can you see? This is a demonstration of the 3D card generations for our method. This one is per-tree model generations. The drag coefficient is 0.27. This is our generations. It can achieve a much smaller drag coefficient. Also, I can show more videos about the trajectory of the car shape change during the optimization. I think one issue is now we use the Gaussian distribution, and it's a unimode distribution. Usually it converges to a simple same local optimal or trapped to the local optimal compared with global optimization techniques. But it is more query efficient.
You mean, so all of them are transforming to the similar shapes?
Yes, this is this batch is 16 samples. It's a whole batch. Usually we optimize this batch together and takes 200 time steps for this batch update. But in our observation, the whole batch converges to the similar shape. But if we start another independent run, it can converge to other shapes.
Yeah, okay. Okay, so yeah, if there's no question, so let's thank speaker again. Thank you.
Okay, thank you.
Thank you for the introduction. I'm Takayuki. I'm our team director of the robot learning team at RIKEN-AIP. Today I will talk about what we are doing in our team recently. Okay. So the use of the robot in daily life have a potential to other social problems such as labor shortages, and also new technologies such as humanoid robots could lead to new industries, and so they have actually a big potential. And however, actually we do not see so many robots in daily life. One of the reasons is that controlling robots typically requires expert knowledge. And that is actually a big barrier to make robots accessible to everyone. However, this might change in near future. So recently, vision language action models are investigated by many researchers. And this model is often called robot foundation model. And these kind of models enables robot control through natural language, such as pick up a pen or move apple or something like that. So if you can achieve this, people do not require expert knowledge to control robots. Then it will make the robot accessible to everyone, probably in daily life. So there are two big factors behind the emergence of the VLA models. One is the scale up of models, and the other is scale up in datasets. So we are conducting research in the field of robot learning with these in mind. So here is a framework for training large-scale models. First, we need data for training a model. So typically, we need a massive data. For example, so there was a project called Open Cross Embodiment Collaboration. And I actually participated in this project. And in this project, researchers from all over the world collaborated together, and we collected nearly 1 million trajectories to create a single data set. And then we train large-scale models, so based on usually the transformer. Actually, we typically use pre-trained vision language models, VLM models. Then, so we fine-tune with robotic dataset. Then we deploy it to the robots. So this is nice, but actually there are obvious limitations in this framework. So here are some videos of the demonstration using the VLM models. Here you can see that robots can be controlled with a natural language, like move apple on clothes or pick ice cream or something. Then so it actually works, but so you can immediately see that task is very simple, like picking up something, and also the gripper is just 2-finger gripper, and also this is just a single arm task. And so here it looks like the system is working perfectly, but actually the zero-shot performance of this model is very limited. For example, if you go to a totally unseen environment, the model does not work well. Then also, when we train this kind of models, we require a massive demonstration dataset, and we perform the supervised learning. So actually, as I said, we have already used nearly 1 million trajectories for training this kind of models. So if we want to have more complex behaviors, then probably we would need much more demonstrations. This is really almost infeasible for a single small laboratories. Also, yeah, so then if we want to have a dexterous manipulation with bimanual task, then it will require much more data. Then also, so when we collect this kind of data set, we actually need to think about strategies for collecting the data set. For example, if the data set contains multiple strategies, then usually the distribution of the action is multimodal. And then somehow the model corpus can happen, and then the model does not work well. So we need to carefully select the demonstration dataset to make the robot model work well. So so there are some important indications from previous studies. So actually, it's great that the large-scale dataset and models are powerful. But on the other hand, supervised learning is not enough for training VLM models. And then we cannot achieve the human level performance just with the current framework. And also, even though if we collect nearly 1 million dataset, 1 million trajectories, we cannot achieve the sufficient zero-shot performance. So this means that training with a pre-correct dataset is almost, it's not enough for zero-shot adaptation in practice. So these are the important indication from existing studies. So this is a pipeline for training the variable models, but it actually poses the technical challenge for robot learning in the real world. So first of all, we have to address a problem like how to collect the samples. And also, then we need to think about how to capture the diverse behaviors during the training. And also, we need to deal with how to deal with a distribution shift when deployment. So I will talk about how we address these components in our team. Okay. Then, before we start, I'd like to think about the difference between the human adults and kids. So actually, the human adults can learn a new skill quickly just by watching others. However, the kids cannot learn a new skill so quickly compared to the human adults. So one of the answers to this question is that so probably the experience. So the human adults have an experience of performing diverse tasks, and actually they have the skill levels internally. Then that's why they can quickly adapt to the new tasks just by watching others or hearing the instructions. Then, so we want to achieve something similar in robots as well. So if we could discover diverse behaviors, then we can have such skills as a repertory, and then we can use them to adapt to a new environment or tasks. So, so to address this, I worked on discovering multiple solutions in reinforcement learning before. So actually, in the field of reinforcement learning, it is known that there are multiple solutions, multiple optimal policies in reinforcement learning. However, typical reinforcement learning algorithm finds single solutions because they don't care about, if you don't care about the downstream task, then single solution is enough. However, so if you think about the downstream task, which might be different from the training environment, then learning the multiple solutions are actually beneficial. Then, so for example, when we think about a locomotion task like this, so the agent can work like this, or like could be hopping, or one-leg hopping, or something like that. So there could be many working styles. Then, so probably some of you are not very familiar with modeling diverse solutions in reinforcement learning. So let me introduce some basics. So typically, in reinforcement learning, we aim to learn a policy that is defined as a conditional distribution of action given state. Then here we write this policy as this. So here we have a latent conditioned part. So here Z corresponds to the latent skill of the task. Then, so this policy shows the different behaviors with different values of this latent variable Z. And typically we use this kind of prior distribution is somehow heuristically designed like. So basically, we use a uniform distribution because we want to have equally good behaviors. Then, so we train this kind of latent condition policy when we model multiple solutions in reinforcement learning. Also, when we train this kind of policy, the objective function usually have two factors. So one is task-related reward term, and the other is the diversity term. So there are some design choices for this diversity term. So sometimes we can use mutual information-based approach, or distance-based approach, or map-leads-based approach. So there are some works in the field of evolutionary computation literature. But so here in our work, so we usually use mutual information-based objective function. Then using this objective function, we can obtain the multiple behaviors simultaneously. So here, this horizontal and vertical axis represents the latent variables. And here, if you change the latent variable continuously, the behavior changes continuously. And so here, the angle of the knee changes continuously. And also, if you change the latent variable in this direction, the agent switch from the two-leg walking to one-leg hopping like this. So we can do something like this in reinforcement learning. And also, we can have a similar result for a different agent like this. So here, we can continuously change the behavior from here to here. And also, we can continuously change the behavior from here to here. So here, we can have multiple solutions for a single task. So here, we just give a simple reward like moving forward or something like this. Then it does not actually specify the unique solution. Then in that case, our method can capture multiple solutions. So here, actually, the solution obtained by this method is not very optimal. So probably it captures many local minimums, but still, I think it works well in practice. Then once we have multiple behaviors, we can quickly adapt to the different types of the embodiment like this. So here, these agents have a different embodiment, but we can simply adapt to the new embodiment just by picking up learned repertories. Okay, so I think that this approach could be beneficial for VLM models in future. But the problem is that to train the VLM models, we usually use a static dataset. We do not use online data collection approach. So we need to extend this to offline setting. So recently, many people are working on offline reinforcement learning like this. So here, traditionally, online reinforcement learning was very popular, and then where the agent collects the data set and updates the policy iteratively. However, in contrast, in offline reinforcement learning, we just did a pre-corrected data set. Then we train the policy and deploy it. So this setting looks a bit weird because we do not iteratively correct the data set, but actually, this is very suitable for applying to the VLM models. So when we train the VLM models, we have a large-scale dataset, and then what is important is to exploit the large-scale dataset first before correcting the additional data points. So with this in mind, recently many people are working on offline reinforcement learning. So we extend this approach to the offline reinforcement learning setting. So here, we could obtain the same result for the offline reinforcement learning as well. So here you can see that we can change the behavior continuously by changing the latent variable. So actually, it's not so easy to extend this framework to offline reinforcement learning setting. In the offline reinforcement learning setting, so we do not have information about the latent variable or skill type. So we need to learn that unsupervised manner. So we developed an algorithm that is analogous to EM algorithms. And we learn the encoder, and then we fix it, and then update the policy, and then we fix the policy and update the encoder, and then so we maximize both expected return and the mutual information. So in this way, we could learn latent variables that represent a skill type, and we can learn the multiple solutions. So here, again, this is a result for the offline setting. So here you can see that two-dimensional latent variables, and we can see that the behavior of the agent changes continuously. So actually, the latent variables are a little bit entangled in the offline reinforcement learning setting. So it's not so easy to disentangle the latent space here. But this is a bit challenging part. So probably if the data set becomes more large scale, then probably we could have some problems like this in future. Yeah. Then so here so far I talk about how we could address data collection or how to capture diverse behaviors. So here I said that when I talk about the difference between adults and kids, that it's about skill repertories. But then we can also see this difference as a training with a pre-trained model or training from scratch. So in this way, so if we see this difference as this, then we can also think about how we should obtain the pre-trained model for general purpose or general embodiment. And so recently we are working on offline reinforced learning for heterogeneous embodiment dataset. So here the idea is that we collect the demonstration from the various embodiments, then we perform the offline reinforced learning. And in this way, we can obtain a pre-trained dataset which could be used for various embodiments. For example, some different type of the humanoid robot or different type of the quadruped robot or something. Then, yeah, so we developed this kind of dataset as a research platform, and then we performed the empirical studies, and we identified the challenge of the cross-embodiment offline reinforced learning. So here in our preliminary experiment, we found that there are positive and negative transfer between different embodiments. And this is very natural results. But, I think this also happens in many multitask learning, in machine learning in general. But then we actually observe the similar behaviors. And here we need to think about a gradient conflict to circumvent this issue. And also, but we are working on this. And also, we have shown that this kind of pre-trained model is beneficial to improve the sample efficiency for training a specific policy. Okay. Then we are also working on some fundamental aspects of the reinforced learning as well to address how to correct the samples. So in a reinforced learning, so we often need to learn a Q function. So Q function represents the expected return. And there are two basic approaches for learning Q functions. And then one is SALSA. And SALSA is an on-policy method that estimates the policy associated with the SALSA is a method for learning the Q function associated with a specific policy. And then the Q function is trained in an on-policy manner. And the other popular method is Q-learning. So in Q-learning, the policy is corrected in off-policy manner. Then we perform the maximization over actions, and then we try to apply the Bellman optimality operator to the Q function. Then we obtain a Q function. So in our recent study, we showed that this learning Q function has two distinctive properties. So one is that max Q backup, it learns faster, but it's biased. Its natural because it performs max operations. Now, on the other hand, SALSA backup is slow, but it's unbiased. And this is also natural result. Then, so this is very simple, but it's actually impactful in practice. Then, so we thought about the continuous transition from max Q backup to SALSA backup, and then we expected that this transition would make the training more sample efficient. Then, the question is how to achieve the gradual transition from the max Q backup to the SALSA backup. Then, so actually, one of our team members developed an algorithm to achieve this, and then he leveraged the expected loss, which is often used for offline reinforced learning. Then using this, then we can achieve the continuous transition from the max Q backup to the SALSA backup. Then we can actually significantly improve the sample efficiency of the standard and popular reinforced learning methods. Okay. Yeah. Then on the third part, we are also working on domain adaptation for robot learning. So domain adaptation is a very popular field in the field, very popular in the field of computer vision, I believe. Then, so we applied such kind of domain adaptation technique for offline reinforcement learning as well. So, and one of our team member has developed an algorithm that applies adversarial training for learning the robust visual features. And then we developed an algorithm that works well. So for learning the visual reinforcement learning tasks. Okay, maybe I speak too quickly, but so here today I just talk about a very short overview over what we are doing. So here what I showed is just about the simulation or small scale things. However, we are actually working towards to develop algorithm for large scale models and data sets. But actually, our recent work are under review, so that I cannot tell you the details, but hopefully I can share more details in a few months. Okay. Yeah, thank you for listening.
So any questions? Hi, Professor. Thank you for your great talk. So my question is about the behavior result part. I'm very curious about how you model the behavior, especially the diversity of the behavior. Is it based on the trajectory or the lantern space? Because to model the behavior is very, very challenging during the sequential decision-making process. Yeah.
So, well, the question is how to model the diverse behaviors in the reinforcement learning, right? So what we are learning is actually just policy conditioned on the latent variables, as I showed in the beginning. So the policy just makes the decisions for each time step. But actually, the latent variable is fixed during the single episode. So in that way, so we do not switch the behavior during the episode. So in that way, we can consistently perform the specific behavior during the episode. So what we do is that we sample the variable latent variable at the beginning of the episode, then we fix it. Then also, the trick we use there is that we learn a Q function that is conditioned on the latent variable as well. In this way, we can learn the Q function that represents the expected return when we follow the specific skew type. Then, so we just learn a single network, but it's conditioned on latent. Then, in that way, we can achieve we can maximize the expected return for each behavior.
I see. So, so it means that at the beginning, your pre-gathered trajectories, they are diverse, right? So it means it cannot be sampled from a stochastic policy, but some predefined or deterministic policy.
No. Well, so in the online reinforcement learning case, what we do is just online data collection. So we just learn from scratch. Then, so we do not require any prior knowledge about the scale. Then what we need is just a reward function for the task.
I see. Okay, thank you very much.
Thank you. Very nice talk. I was trying to understand, you said quick adaptation.
Mm-hmm.
And I mean, the slide 6, this analogy is I'm a bit troubled by that. And we could talk about that later maybe. But I think when you're saying quick adaptation, you mean you want to do it quickly because you don't have too much data, right? Am I understanding it correct?
Yes, so when I talk about the quick adaptation, it's that I don't want to perform the trial and error thousands of times, just probably a few times or something.
I see. Yeah, but I think quick adaptation depends on plasticity of the model that you're trying to change, right?
We do not change the model parameters. We just choose the value of the latent variables. So
no, but you're saying that it's the experience that makes quick adaptation possible, and I disagree with that.
Okay. Probably
because I think too much experience makes it worse. You know, I haven't learned Japanese in 9 years, and my son is much better. He's just 2.5.
I see. Probably the expression in the slides were not very good. So maybe, so I said that in the slide, I have an expression like the expense is equal to skill libraries, but probably that is not equal. That's what you mean.
So then I'm trying to understand, like when you say quick adaptation, I would think that somehow the system is ready to, you know, absorb as much as information as possible from fewer sample, right? So then, for me personally, it's about the capacity of the model and its readiness where it is. Like if the model is like learning to walk and then you ask it to suddenly, you know, do something very different, like run in a very weird way, then it cannot do it. If you have slow changes, perhaps it can adapt slowly. Okay, so just getting to my question, like I don't see in this RL framework, in the whole talk, I didn't see any talk about how this kind of curriculum would be added so that the quick adaptation is possible. So I don't understand why applying an RL problem or RL framework to this problem will lead to quick adaptation. I understand that you have prior knowledge somewhere and you're trying to inject it, but that is a very rigid way to kind of add quick adaptation there, right? And so I'm just trying to understand why this framework is a good framework for me to think about quick adaptation.
So here, what we do is that we learn latent policy that is conditioned on the latent variables like this. And then in this way, we can model the diverse behaviors in a single model. And then during the quick adaptation, what we do is that we simply try out the multiple behaviors and then pick up the best one for the test environment. So in that way, we do not have to change the model itself, but what we change is the input to the model. Then in that way, we don't have to care, not care about, but we do not adopt the model itself, but we adopt the behavior type. So probably it's, so learning plasticity is important when we adapt the model parameter itself, right? So during the training, sometimes the model plasticity is decreases.
I think I understand. You're saying by keeping multiple solutions, you make it easier to adapt because there is some plasticity in that form. I see. Okay, thank you.
Thank you for the question.
Thanks for the nice talk. So my question is a bit vague, but so simple real is always a big issue in this topic. There must be several options for this, like improving simulators to make it more realistic, or improving real robot to make it more noiseless, or developing a method that fills the gap in sim and real. So which one is most important now?
Well, probably using simulation is important to reduce the training cost because so in the physical world, we cannot parallelize the training, but it's very easy in the GPU. But on the other hand, actually, we need to think about sim-to-real gap. So probably simulation is important to obtain somehow decent models. Then we actually need a phase to fine-tune the model for the real world. So I would say the both trainings are essential. Then so recently, so there are, in my opinion, there are two schools of this approach. So some researchers in NVIDIA likes to use the simulations. Then they try to address the problem from the simulation side, like employing the domain randomization and then parallelize the environment and then try to create a massive synthetic data. But on the other hand, the people like the researcher in UC Berkeley or physical intelligence, they are they prefer to use the real world data. Then, so actually, if you directly use the real world data, then we don't have to care about the Shimizu real gap. So actually, there are two approaches, and actually they are trying to merge at some point, but I'm not sure whether I
So as long as you have enough real data, you say you don't need simulators.
Yes.
One school of people.
Once we have a sufficient data set, that might be
in
the
that case, everything is
still,
offline, right?
Yeah, everything is offline. But still, so even if we collect the real world data, still we need the domain. We need to cope with the domain adaptation.
Right.
That's also the problem. So probably what is more fundamental is how to address the domain shift from the training to the test environment rather than simulation to real world.
That's more significant, you think?
Yeah.
I see. Okay, thank you very much.
Thank you for the talk. I have a question about this object function. So maximizing data J of Q itself is already non-convex optimization, right? So is it possible that there is some hyperparameter if you tune the hyperparameter, change the hyperparameter, and if you only maximize the task related reward term, you can obtain different policy?
Yes.
And then you can ensemble them. What's the relationship between if you learn some latent variable conditioned policy with if you learn use many random seeds, learn 100 policy and then ensemble them, you can also maybe have a quick adaptation or.
Yeah, right. That might be possible. Well, so regarding the first part, so actually, if you use different hyperparameters of the reward or diversity term, you will obtain different solutions. Then, so even if you use the algorithm, that's
I mean, without the diversity term, because if I understand correctly, you must use your special policy. That pi must depend on the latent variable z. Then you can have the diversity term. You can maximize that one. If I use the traditional policy, I only have pi of a action given state. Then I maximize data reward because now the model is deep neural network and the maximization is non-convex. So by changing the hyperparameter, I can obtain different policy. Then I can ensemble them to get like a mixture of expert solution, something like that.
Yeah, that's actually possible. Actually, such an approach is more popular in the evolutionary computational people. In that approach, as you said, we simply train a policy that is just conditioned on state.
Yeah.
Then it's not conditioned on latent variable. There, we simply generate a mini
a lot
samples
of initial solution
with different initialization or different locations. Then, so what we can measure is that the distance between different policies. So even though they are not conditional latent variables, because we can measure something like carry divergence.
So you will not really have a diversity if you use many random seeds and obtain many policies. Maybe the policy will be look similar.
So if you do not have the diversity term, it could be different policies. And actually, it looks that it obtains a different locomotion types. But it's better to maximize the diversity term if you want to obtain a diversity behavior.
I see.
But actually, so this kind of evolutionary approach measures the distance between the two policies and then maximize the diversity.
Okay, I see. Yeah, because in that case, I can have many policy and I can ensemble them. And in your case, you can also try to use different latent variable and you can ensemble them. Or I don't know, because when you decode or when you generate the trajectory, at each time step, maybe you can try to ensemble different pi of a given x and z with different z, the same s, and you can have some mixture distribution as the ensemble the pi, and you generate the next action. Or you can use some heuristic search algorithm. I mean, whenever I regard it as multiple policy, I can have some better encoding, decoding algorithm.
Yeah, actually, that's an interesting direction. Actually, we can think about how to mix the learning behaviors. Okay. That's also possible. But here in this work, I didn't think about how to mix them.
Yeah, you fix the latent variable and generate the whole trajectory.
Yeah.
Okay, thank you.
Yeah. Probably, but so let me add one point. Here, so when we learn continuous latent variables, and if you learn a good latent space, so typically well, so if you choose the latent variable here and the behavior on here, and then so usually the behavior somewhere around here or some probably around here is a kind of the mixture of these behaviors. So yeah, so it depends on what kind of latent space is learned.
Okay, thank you. So maybe I think we had fruitful discussion. So let's thank speaker again.
Thank you, and thanks for the invitation. Yeah, I will speak about our recent research on using variational Bayesian methods to improve deep learning and also LLMs. As a quick motivating example, maybe here's a prompt that you might give to one of these models. Alice eats cereal for breakfast 4 days a week and pancake 3 days a week. And then we want the model to answer, this morning Alice had A, cereal, or B, pancake for breakfast. And we asked this to Llama 3. And the model was very certain the next token probability for A was 1.0. So the response is A. But this question is ambiguous, right? We don't know which day it is. Alice could have had both cereal or pancake. So an ideal model, and we will see that the variational models, they are more in uncertain situations where the question is ambiguous, they take multiple solutions into account. So these models, they will say something like A, but also maybe B. So the probability of the next token is maybe 60% A and 40% B. And this is the classical way that Bayesians motivate their existence, but actually this is, for us, it's just a small, nice bonus. And I hope to show you that in this talk, that Bayesian learning offers much more than just this kind of improved predictive uncertainty. So it helps for regularization and generalization. It's very useful for continual learning, model merging, fine-tuning. Can also do the zero-order fine-tuning with that we've seen in the talk before the previous one. I will particularly focus on federated learning and present a recent work where I show that this kind of Bayesian learning can really improve federated learning, and it's, yeah, the list goes on. So there is, it improves all aspects of machine learning. So there's no reason why one should not do this. That's hopefully the message I can convey today. And yeah, so people say, okay, Bayesian learning doesn't scale, but it's actually a misconception. So what we've published, this was last year, ICML 2024. We can train very large neural networks using variational Bayesian learning by just changing a few lines of PyTorch code. And yeah, on the right, you see the classical convergence plot where we plot the validation perplexity. So this is some kind of test loss versus the training steps. And our method, it's a Bayesian learning method called IVON, improved variational online Newton method. It can match the performance of Adam or even improve it. So the larger we make the models, the better it seems to get. There's a slight overhead here, mostly due to implementation issues, because the Adam implementation is very optimized in PyTorch, and we wrote more like a researcher code. So there's a slight difference in time, but it almost matches the training speed. And there's no memory overhead. So it has the same memory cost as training with Adam. And what you get on top, you have here the blue line on the simple toy example. This is your Adam training. And here, okay, this is an earlier method called Wogen, but it's very similar to IVON. And what you get instead is all these thin red lines. So just in a single training run, you don't need to do any deep ensemble or anything. It's just changing one line of PyTorch code. You're actually learning multiple diverse solutions to your problem. So in regions where the data does not specify the solution, you get all these random red thin lines by sampling from a posterior distribution. And this is really easy. You can install it. 12,000 people have downloaded it so far. I hope this number goes up much more in the future because we think this is a really good method. And you essentially just have to comment out your Atom optimizer in PyTorch, comment in this new method that I will explain in this talk today. And you have to add one extra line in your training code where you're taking random samples from your posterior, and a second line if you want to take multiple samples, which slows down the training but further improves the solution. So it's very easy to use. And then if it's so easy and cheap, is it accurate? It's a valid question, but it's actually one of the world's most accurate approximate Bayesian methods. So we won this NeurIPS challenge on approximate inference. This was already a few years back. We used a version of this optimizer to win the competition. And what was this competition about? They computed the exact posterior on 512 TPUs over 2 weeks, and then the goal was to get as close as possible to it. And we ranked better than competing Bayesian methods like SWAG or some kind of deep ensembling, efficient deep ensembling method. So it's cheap, it's easy to use, and it's also very accurate. And then the question is, what kind of cool stuff can we do with it in deep learning? But before I go into this, I explain a little bit. Maybe if you haven't heard this variational training or Bayesian learning before, I quickly explain to you what is the difference to the standard training that you're all used to. So if you do standard training, you optimize over your model's parameter, theta, some loss function, maybe a weight decay, L2 regularizer. What we add on top is essentially everything in red. So in this talk, when something is red, it means it's something additional you have to do on top of the standard training. And what we add here is something called the expected loss and an entropy term. And we also change the minimization variable from theta to Q of theta. And so we search for a probability distribution over the parameters to find multiple diverse solutions that we can sample from that Q of theta. And these thin red lines that you see, these are all random samples from our Q that we estimate here. The expected loss term essentially says that these random samples that we draw, they should have low loss. So if you just minimize that, we would collapse to some minimum. And that's why we have this entropy term. It's a diversity term that says our distribution should be spread out. So we capture multiple diverse solutions. And having this Q of theta available, this is essentially what you get on top if you train with I1. We can use it for many, many things, and I will particularly focus here on federated learning later, but I will also show some fine-tuning examples. The method itself is actually it's a bit more technical. It's a natural gradient descent, actually not so different from the method we've seen 2 talks ago, where we do a natural gradient descent on the parameters of the Gaussian distribution of the expected loss, but we additionally have an entropy term here. And if you do this natural gradient descent on the Gaussian and you rewrite it, it turns out it looks almost the same as the Atom optimizer, with differences highlighted in red. So if you take the Atom optimizer, or here it's RMS prop, because I removed the gradient momentum for simplicity, then you do the red terms, you do these changes, and then suddenly you're not optimizing L of theta plus R of theta, but you're suddenly optimizing the red objective on top. And the main changes is that during training you sample from that posterior distribution that you estimate. The squared gradient is replaced by some stochastic quantity. So that's actually an unbiased estimator of the expected diagonal Hessian. That's why we call this a Newton method. So it's really using the Hessian information rather than the squared gradient. And we divide by h rather than the square root h. So these are the changes. And then for your neural network, you get for every connection strength in your neural network, you get this little Gaussian distribution, which has a mean and a standard deviation. And then you can sample from this and you get many random diverse solutions that all provide plausible explanations to your data. So I will just go over some recent work which has been using I1. This is actually a paper I'm not part of, but they got great results. with that method, and it's very intuitive to explain what they did. So that's why I put it. So we have a large visual question answering model where we get an image and also a text. And the question is basically, does the pedestrian light say walk? And I think I don't see it actually. It's here. It's a bit small, but there's a stop sign. So the correct answer is actually no. But if the Adam trained model, it's very confident that the pedestrian sign says walk. And this is, of course, catastrophic if a model makes such a mistake. And if you train with this I1 optimizer, you actually get more. Okay, it still says, yes, it should walk, but it's actually below a certain threshold. And then the model can abstain from answering and say, okay, I'm uncertain. So I actually don't know what this light says. And the opposite situation is also possible, that the Adam model is actually uncertain when it's clear that outside there is a dog. And it also provides a better calibration in the other direction, that it can give the correct answer in a very certain situation. It's also very effective for fine-tuning. So this is for a llama 2B model, some standard data sets. We got very large improvements in accuracy over the Adam training and related Bayesian methods for LoRa fine-tuning with I1. And what's very fascinating is that the longer we train, the better it gets. So if you fine-tune your LLM with Adam, the performance stagnates. So it goes up a little bit, but then the performance just stagnates. And what we found is with I1, the longer we trained, the better it gets. And I will go a bit later maybe into some explanation, but it's related perhaps to something that people also call grokking, that you find a solution at first to your problem, and then the longer you train, the solution gets simpler. And because you're optimizing also over this entropy term, you have this kind of complexity bias towards simple solutions. So it finds solutions that generalize better over time. So it's a very nice scaling with training compute, which aligns with the recent trends. It's especially good in situations when there's very little data. So when the data does not fully specify our model. If you just train on 256 training examples, the gap to the Adam solution is very big. And the larger we make our training set, the benefits get less and less with that method. We can trade off accuracy and calibration by doing the sampling from that posterior that we get, ensembling multiple random solutions. And depending on the temperature that we use for that sampling, we can either get very high accuracy but decent calibration, or we can get very, very good calibration at a little bit of cost of the accuracy. You can see these are competing recent Bayesian methods, blob and Laplace approximations. These competing Bayesian methods, I think MC dropout is also somewhere very down here. They are below this kind of Pareto curve that's traced out by I1's posterior. So we strictly dominate existing approaches. We can also use that Q of theta that I1 estimates on top to improve the LLM decoding. So typically, if we want to sample a text from a language model, we sample a random next token, and then it provides a generation. And typically, one samples just from the softmax layer at the end of the LLM. But instead of sampling from the softmax, you can actually sample from that posterior distribution that one estimates, and then sample from the softmax. And because one gets more diverse solutions, one can combine these solutions together with a procedure called minimum base risk decoding, and to combine all these diverse solutions and find a single good answer. And here we found that, okay, if you use a single model for this minimum base risk decoding, so this is just sampling from the softmax probability distribution in the last layer. For machine translation, the bleu score, for example, is 19.7. But if you sample from the weight space posterior during decoding, the translation quality goes up by 1 point. So this 1 point is not something small. This is actually a human would notice that this is a better translation. So for free, we get this Q of theta, and we can use it during decoding, and it just gets noticeably better the answers. So this weight uncertainty is really useful for this LLM decoding. And we found this here also, that this is something that people call test time compute, that instead of having the model just generate one answer, the model thinks, or thinking, or just samples many answers and then somehow smartly combines them. And here we have the kind of the test time compute, like how many answers we let the model generate. And we can see that for the softmax probability sampling from Adam, this kind of test time compute scaling, it somehow saturates much earlier than for I1. So during test time, if we sample from that posterior distribution, we get a much better scaling with the test time compute. So what I eventually hope to show in my research is that this kind of variational Bayesian learning is just a much better idea for deep learning. And that should reflect in improved scaling laws, that just by using the same compute, we can just get much better results than the existing methods. And I'm not there yet, but hopefully this would be a very convincing demonstration, and maybe people might switch to variational learning. Okay, then of course the question is, okay, this sounds impressive, but why does it work better? Why should it work better? And here's an explanation already from 1993. Geoffrey Hinton wrote this paper, Keeping Neural Networks Simple by Minimizing the Description Length of the Weights. So he already proposed that objective function that I was using in that I1 is optimizing. And the motivation here is that by having this entropy term, you're essentially trying to find the simplest solution that explains your data. And that corresponds to flat minima also in the loss landscape. So here's a very simple two-dimensional loss surface. Bright is very high loss. We don't want to go there. And dark is low loss. And if I train with SGD or Adam or something, I really go here to the lowest dark place. If I train with I1 instead, I actually don't go here. I move to this point. And this point is much flatter. It's actually not a minimum in the strict optimization sense. The gradient here is not zero of the loss, but it's still very low loss. And it can put a very large circle around its solution where that loss is still low. So we found a simpler solution. So I can encode this point in much less bits than I can encode this point. Because if I encode this point and I make a small mistake, suddenly my loss is very high. But if I make a small mistake here, my loss stays low. So these flat minima, they correlate with generalization, and there's some relation to Occam's razor and so on. So these are good. And we had a work now next week at NeurIPS. We will be presenting it, which proves that I1 finds actually flatter solutions in a regime called edge of stability. So this is a popular way to analyze the bias of deep learning solutions. So deep learning is a non-convex problem, so there's many solutions. So how can I bias my training to a good solution? And what people found is, okay, if I train with a very large learning rate, I get solutions which generalize well. And it turns out that if I train with learning rate rho, then the largest eigenvalue of my Hessian, which is called sharpness, is around 2 over rho. And of course, I want to make my learning rate as large as possible because I want to be as flat as possible, but at some point, the process becomes unstable, and that's why we call this edge of stability. Just right at this edge of stability, we have this 2 over rho flatness. Now, if we train with I1 and we fix the posterior variance to 0.05, we find that the largest eigenvalue of the Hessian is much smaller. And if we set the variance to 0.1, the sharpness is even smaller. So is there a similar theory that tells us, okay, this will be around 2 over rho? And this is the contribution of the paper, that we have also a theory which predicts the sharpness of the training with I1. So the largest eigenvalue of the Hessian predicted by the theory is very similar to what we observe in practice. So our bounds match the empirical results. And the main idea for this whole edge of stability literature is actually to do the analysis on a simple quadratic loss function, where this Q is just the curvature of my quadratic. And then we all know from optimization that I converge on my quadratic, I go to the minimum if my learning rate is less f2 over rho, so rho is my learning rate in gradient descent. If all the eigenvalues of my Q are less than 2 over rho, then I converge to the minimum. And if I use a larger learning rate, I will actually escape from that quadratic. If in I1, we have an additional noise injection. So we have these kind of posterior variance. And as you can see, if I increase my posterior variance, then the whole process becomes more unstable. And I escape easily from a quadratic that gradient descent would actually converge to. And there's also the number of samples used in that estimator. If I increase that, it gets more stable. So few MC samples and large variance, it's like the most unstable regime. And then we have this new theory which says, okay, you still have this 2 over rho factor for I1, so you should still use the large learning rate to go to the flat minimum, but you get an additional variational factor, which is less than 1, which depends on the number of MC samples and the posterior variance. So these are the sigma I squared. And this bound here, this predicts the sharpness, and we've seen on the previous slide that it matches the empirical observations. So this is one explanation why we observe these nice results. And in the last 7 minutes, I will talk about federated learning. So this is another topic where Bayesian learning is very useful. And we have this recent paper. It's not published yet, but it's online, and the code as well. And I want to quickly convince you that variational Bayesian approach is also very good for federated learning. And so why is having this uncertainty important in distributed or federated setting? So typically we have these kind of k clients, each minimize their own loss function. And then the question is, what information should be exchanged between the clients? And there's a very simple example. We just want to compute the mean of a bunch of numbers, xi, and each client has some numbers. So first client has 1, 2, 3. Second client has, it computes its mean, has 2. The mean of 1, 2, 3 is 2. The second client has these numbers. They add up to 30, and then 30 by 5 is 6. And the question is, should these two clients, should they simply exchange 2 and 6, and then the server average the solution? So that would be 4. But if you compute the mean of these numbers and divide them by 9, you will actually get 4.5. So simply exchanging the mean and averaging it is actually a bad idea. And what you should communicate additionally is the posterior precision. So this is the related to the Hessian here of my loss, and it's the number of data examples. And if the clients communicate their solution and the number of data examples, they can average them and converge in a single step. But and this is also on a different example, 2D logistic regression example, where we have an outlier on one of the clients. And then the first client is really affected by this outlier. And then it takes 5 communication steps to correct that result because the other client is very easy. And the other client says, okay, you should go here. But because it made a mistake at the beginning, it takes very, very long to correct that mistake because it was really certain that the decision boundary should be here. And then it's very slow to adapt because it really over-focused on this outlier. With the Bayesian training, you get these gray dashed lines. So it's kind of wary already of this outlier. So it says, okay, maybe the solution is here, but I'm actually a bit uncertain. And then in a single communication round, it can adapt to the correct solution, just because it's more open-minded about this outlier here. And then the other client says, oh no, I'm very certain I should be actually here. And then it can adapt in a single step. So having this weight uncertainty for federated learning should really speed up the training and improve it. But current federated learning methods don't do that. They simply do this averaging of the parameters. So they federate averaging, they minimize locally and average. And then there's modifications to that, fed procs, and also an old method called ADMM. So these methods, they only consider the parameter estimates, and they don't consider the weight uncertainty. And what we did, actually, I'm running a bit out of time, so I will wrap up quickly. What we did is we generalized this federated ADMM, which is one of the state-of-the-art methods for federated learning. we generalize that method to optimize over probability distributions instead. And essential to that is to kind of exploit the duality structure that's inherent to ADMM, which uses dual variables. We extended that to some kind of this, duality on the space of probability distributions. And again, one has to make some modifications here to ADMM in red to have this kind of Bayesian version of it. But they are very simple. And there's two things I want to emphasize here. So the first one is that here these VKs, these are Lagrange multipliers in ADMM. This is this kind of a linear term. Now this gets replaced with this kind of nonlinear term, where you have this mapping T in there. Maybe I didn't explain what this is, but essentially these dual variables, they carry much more information than in the classical setting. So the clients can exchange more information. And the important thing is that we have these kind of dual coordinate systems that I didn't have time to get into, but essentially this is our new optimization algorithm. So there's been 30 years of research on ADMM, also generalizing it to Bregmann divergences and so on. And after consulting with many optimization experts, this really turns out to be a fundamentally new and meaningful extension of ADMM, where in the Lagrange multiplier update, one jumps to the dual coordinate system. And this has somehow been missed in all these years on research on Bregmann ADMM methods. So we are very confident now that this is a fundamentally new method for to generalize ADMM to Bregmann distances. And it gives us new Newton-like or Adam-like ADMM versions. It's easy to implement. And this is the final slide. We have here a federated learning setting with 100 communication rounds. We look at the best non-Bayesian methods. So we run all these methods: federated averaging, federated prox, federated ADMM. So this is called DUN, but it's an ADMM method. It's an ADMM-like method. And the best Bayesian method gets to around 40%. Then we implement a partitioned variational inference method from 2022 using IVON. And we already get much better results. And then our new Bayesian ADMM implemented with IVON gives even faster convergence and better results than this partitioned variational inference. So it not only works in toy settings, so this is a ResNet on CIFAR 100, and it gives good results there. So that's it. Thank you very much.
So any questions?
Thank you for the talk. I have two questions. The first one is, you have a slide comparing some non-Bayesian optimizer and the Bayesian optimizer.
This one? Or?
No, the previous one. You have some code. You're showing that it's very simple. Yeah, I'm wondering, that one?
Yes.
Yeah, maybe this is also okay. It looks like you have two regularization. One is for theta and one is for Q.
Yes.
So the one for theta, is that mandatory or optional?
It's optional.
It's optional. Oh, okay, thank you. Then for the federated learning part, I think because the two baselines in your slides, in your presentation are a bit old. I think in federated learning there are a lot of work they consider the discrepancy between the local loss landscape and the global loss landscape, and they have some smart tricks. I say because it's not a theoretical, it's tricks. There are tricks and to enable the local client to be able to estimate or just imagine what the global loss landscape is in the client without seeing other clients' data. In that sense, they are also, even so, they are non-Bayesian, but they are also able to avoid the bad case you show.
Yes, I agree. And so there's two answers to this. So one is you could do these tricks on top of our method. And we wanted to have a kind of a principled approach and see, kind of compare it to other principled methods without tricks and see the improvement. The other point is that these methods might be secretly Bayesian. So they might say, okay, I do these tricks, I try to estimate my loss landscape around my minimum. So there's the sharpness-aware minimization stuff, for example.
The motivation of those family of a series of methods are simply they want to push federated learning closer to the original centralized training.
Yeah.
Because if it's in centralized training, you have so many clients, and a single client has a very bad outlier.
Yeah.
By looking at other data, they can know this is outlier and try to avoid it, right?
Yeah. So these are related principles, and here they come from a coherent framework. And of course, you can come up. So a fundamental method, of course, it appears in many disciplines. So these Bayesian approaches, they're also related to maximum entropy, minimum description length. So it's not like the Bayesian view is the only view, but this is like just something fundamentally good that you should do, and it appears in many different fields. And here I call it Bayesian, but I could also call it maximum entropy or minimum description length or something else. So what I'm saying is that the methods that you describe, they might appeal to the similar principles that also appear in the Bayesian approach. They just don't call it Bayesian, but they use similar principles.
I don't think so, because they are still focused on the original centralized training. If the centralized training is non-Bayesian or non-SAM, it's
yeah, but somehow this is what these Lagrange multipliers try to do actually. These lambda hats, they try to model the global loss function. So where is it? Here. This lambda hat. It's a Lagrange multiplier, but you can see here. You can see it. It's a kind of a finite element basis function thing. So if this t is theta comma theta squared, this is a quadratic approximation of the loss function. So you're trying to model the global loss function here. It just appears through a principle.
Okay.
So it's also trying to do this global modeling here.
So it means you can inject some other information, not necessarily the margin or the uncertainty you show. Oh, okay. Okay, thank you.
So the combination of the R and entropy is actually the K divergence from Gaussian. So it seems meaningful, or it's just optional. So
it's optional. Yes. So this comment here is that expectation R minus entropy, you can write it as a KL divergence to a prior. But the true prior used in deep learning is not the one that we put here in R. So typically R is a very simple quadratic. But deep learning optimizes a different prior through implicit dynamics and so on. So it's somehow misleading, actually, if you would call this a prior, because the actual prior that you're optimizing is hidden in the dynamics of deep learning.
Thanks for the great work, and I think the variational one is very useful. My question is that in page 7, next page. So the I1 introduce another hyperparameters, the tau, right? So how you choose the tau? Is it related to data sets or parameter sets?
You don't want these weights to be too noisy. Then you are adding too much noise to your weights, and then the training diverges. So you want to set the tau such that you add a small number, because the sigma depends on tau. So the larger you make tau, the smaller the sigma gets. So if you make the tau too small, you're adding a lot of noise, and then the training diverges. If you make the tau too big, you're essentially a deterministic SGD or Adam-like optimizer. So you want to be right at that sweet spot where you add kind of edge of stability-like amount of noise, where the training still converges, but the noise is meaningful. Okay. So this tau parameter, it's you have to tune it such that it depends on the network architecture, the data set, such that the training is stable and converges well.
Another question is that this algorithm introduced the entropy and you said in some sharplist, I don't know why this using this entropy could relate it to have wider better sharplist. I don't know why it's
So for the Gaussian, the entropy is the log of sigma. And then it basically wants to make the sigma bigger. And if the sigma gets bigger, you're adding more noise to your weights. And then it still wants to find a low loss. So that's why if you add a lot of noise and the optimization still wants to minimize the loss, you necessarily end up in a flat place.
Okay, I understand now. Thank you.
Sorry. I have a quick question. So maybe from the viewpoint of Bayesian statistics, maybe the optimal one is the real posterior distributions. So then we can consider like between your method and like a posterior distribution. You consider like a variation base on the Gaussian distribution. We may consider between them like a mixture of Gaussian, something like that. So then my question is, do you think it is better to if we can compute, so then it is better to compute like between them, or like a variation base restrict your model to like a more simpler model, so then it can act as like a regularization. So what is it?
Yeah, it's a good question, and we actually don't know the answer. So this is the only example of variational base that we have that works well. But my intuition is that it should be better if we make it more expressive. But also purely from optimization perspectives, if this one becomes non-diagonal, then this becomes like a K-FAC or shampoo or Mingyuan-like method. And these methods work better at optimizing. So the non-diagonal preconditioning in optimization works better than the diagonal preconditioning. So just from that optimization viewpoint, it should be better. And the statistical one, I'm not so sure because there's no proper Bayesian model. There's no likelihood. It's deep learning. So then it's hard to make any statistical arguments. But just purely from computational arguments, I think it's better to have more expressive posterior.
Okay. Fascinating talk. Thank you. So the way you present it, it sounds like that's it. You've solved it, right? So it sounds great. I mean, I'm Bayesian as well, so I do believe that everything's Bayesian in a way. So, but my question is, so what are the challenges that you're facing here?
Yeah, there's many challenges. So one of them is getting people to use it, because typically we give it to people and they say, oh, it doesn't work. And the reason is it's not so easy to tune the hyperparameters of that method. So that's one big challenge. And that took also a long time in deep learning. People were saying deep learning doesn't work, and then people figured out the little tricks, and now it works. And here maybe this is really a bare bones Bayesian method, and the variance of this estimator is very high. So this is very noisy. So there's many possibilities to improve it, using importance sampling, some marginalization in the last layer, and like there's tons of things to improve this. This is just the most simple bare bones thing, and with a lot of tuning, we showed it can work really well. And now the big challenge is to make it really reliably always work well. And that's why people like Atom Optimizer, it always works. And here we need still a bit of tuning. So if we can manage this, I believe people will really switch. But it's a big challenge, of course.
Thank you.
Okay, so it's a good time to end this session. So thanks, speaker, again.
Okay, good afternoon, everyone. Really happy for you to still stay here and listen to my talk. Today I'm going to present what does adversarial defense need to advance, especially for diffusion models. So I'm actually from TensorLearn team in RIKEN-AIP, and my PI is Qibing Zhao Sensei. So before we start, just have a really quick recap on why adversarial defense is important and why it originates. So basically, defense means we want to resist the adversarial attacks, and the adversarial attacks are actually targeting for the vulnerability of deep learning models or classifiers. So basically, for human perception, it's very easy for us to identify this image as a panda. So after some human imperceptible perturbations, still for us, after this small perturbation, we can recognize this one as a panda as well. But for deep learning models, it's going to be really manipulated and say, this one is a gibbon with 99.3% confidence. So basically, this is one really important thing for this decade, that basically this inconsistency on the perception between human and machine learning models is creating lots of troubles in real practice and also in theory. So one important thing for us to address today is how to avoid this vulnerability for deep learning classifiers using generative models. So before we move on, I want to highlight the target, or sorry, the key to avoid this vulnerability of deep learning models towards this adversarial attack. So basically, the core idea to find the answer is to find the true semantic label within this adversarially attacked example. So basically, even given this attack example, where deep learning models can classify that as a gibbon with very high confidence after the defender is what we designed as a model, then we can still identify this image correctly for this true semantic label as a panda with also very high confidence. So how to find this true semantic label becomes the key goal or task for today. Any questions here? Are we on the same page? Okay. So there are some ways, lots of ways actually, to defend against these adversarial attacks. So this group of methods for defending is called adversarial defense, of course. So actually, until today, we had two tracks as defenders. The first track is adversarial training, and second track is adversarial purification. So for adversarial training, I'm basically directly targeting to this deep learning models as a classifier. So basically, we want to train this classifier to change its decision boundary to correctly identify this adversarial example still as the true semantic label as a true label. Yeah, so basically, it relies on generative attacks. This attacks has to be generalizable to cover as many adversarial attacks as possible. But at the end, it still has its limits. So basically, the defense is only against these attacks, which are trained on these classifiers. So the significant robust accuracy decay will happen when they defend against these async attacks, which are really complicated and really, let's say, newly published and proposed. And the other way is very sophisticated but very effective in recent 3 years, which is called adversarial purification. So in adversarial purification, we rely on the powerful generative models to generate the clean images based on the given adversarial examples. So basically, no retraining is required for classifiers, which means that lots of power for training these classifiers can be saved. And also no assumption for the threat models as well. So any attack can really happen there, but we can still resist it successfully. So basically, it means we can defend against these unseen attacks. Any questions for this page? No? Okay. So there are some details on the adversarial purification models. So basically, given these adversarial examples, we use very powerful generative models, as we discussed before, to generate clean examples. And this generative models' performance are relying on the powerfulness of these generative models, of course. So in the past, people use GANs, energy-based models, or score-based generative models, but they all appear to be not really powerful, and suboptimal results come from them. But happily, we have diffusion models from 2022 applied for adversarial purification. So basically, it means we can generate successfully for clean images, which are high in fidelity and also really correctly classified by deep learning classifiers for its true semantic label. And then basically, our discussion will start from diffusion models scope. Any questions, comments? No? Okay. So the canon for diffusion models for adversarial purification is proposed by Wei Nia's group in 2022. And I think this paper is actually from NVIDIA, so they are really rich in experimental results to prove that they're powerful for adversarial purification. So basically, the whole design is very simple. They just directly use diffusion models, but they change a little on the level of noises. Specifically, in the forward process, we just add noise as we did in diffusion models, but we stop at a certain level. which means I want to keep this semantic information not fully perturbed and fully changed or covered by this Gaussian noise. And then from this partial Gaussian noise, partial adversarial example mixture, we do the reverse process to denoise. So because adversarial tags are basically diffused in the forward process part, so when we're doing denoising, we're denoising Gaussian noise together with adversarial tags together. And then at the end, we have the clean images where adversarial tags and Gaussian noises are fully removed. This is where we can have the clean images for the downstream process for classification, where we can have the true semantic label. Any questions? Comments? Okay. Yeah, so after, or kind of like at the same time, there is the other group of methods for diffusion models for adversarial purification secretly started to grow, which is called guided diffusion models for adversarial purification. So here, guidance becomes very important to change the reverse process and try to have the generated clean images following our goal to have a high fidelity together with high robust accuracy, which means given a adversarial example after some process for defending and then later for very high classification accuracy. Yeah, so in this case, they added guidance simply as a difference between the reverse processes value and the forward processes value at the same level of noise. So the reason is that they still want to keep the semantic information, but they do not want to control the level of noises. So in this way, they don't really have to fine-tune this T star, which means the level of noises in the forward process. As long as they keep the small distance, they can have the semantic label information implicitly kept. And in the later process, for the denoising or reverse process, the image fidelity will still be increased. So later, they can use the pre-trained clean classifier to correctly predict the true semantic label. Any questions? Okay. Yeah. So following all the past ideas, in ISML 2024, we proposed a contrastive guided diffusion model for adversarial purification. So basically, from our analysis, we draw one really important conclusion is that diffusion models do demand the contrastive guidance for adversarial purification to advance. So let me give a very short summary here is that to keep and to find the true semantic label information, basically we want to do as what we see in the past. I want to keep each step or keep the semantic information across different steps of the reverse process as much as possible for the same image. But for this image compared with other images, we want to separate them as much as possible. So the semantic label information won't be mixed up together. So in the downstream process, we can easily classify them correctly. So to elaborate it, let's move on. Actually, this whole work is from a very good theoretical insights proved by Wei Huang. Thanks for him. So basically, we put on one assumption following the feature learning's paradigm is that we assume we have two classes of data which are linearly separable. So here we only analyze on a binary classification case. The data model is assumed to be in this way. So basically, we assume data is a combination of the feature or signal, which is mu, plus the noise, which is annotated as psi. So Y here means the label, because it's binary classification, so either is +1 or -1. And when we have the high dimensionality cases, we also assume the whole data is linearly separable. So we have also a number of samples which are RID. And here we use them to train our later classifier. So any questions on this assumption? Okay. Cool. So basically, we adopt a linear classifier because we assume the data are linearly separable. So basically, we follow the least squares method to derive and to find this linear classifier, which is derived in this way. So basically, in the high dimensional settings, this theta star, is also the correct classifier. For detailed derivation, then we welcome you to check. There's one paper proposed by, written by Yueming, and this one is basically on adversarially robust generalization requires small data. More data, not small data. Yeah. Any questions? Okay. Yeah. So given this correct linear classifier exists and also the past assumptions, so now we consider adversarial example, which is constructed in this way, which is actually very standard combination or construction of the adversarial example, because here we have the original clean data and here we also have the adversarial attack. So basically for adversarial attack, we have a very natural assumption that it comes actually from the design from the psi, the noise part, not really from the signal part. The reason is that if we attack from the signal part, then we have to reverse this label. So lots of costs are there, and the L2 norm between the adversarial example and the previous clean example will be very large as well. So basically, we actually attack or build this attack from the psi, the noise. So basically here, SNR means the signal-to-noise ratio, and N is a number of samples, as we discussed before. So basically, this attack should be very small. So in practice, it's also consistent. So think of one case that when we are actually attacking one image, as we saw in the gibbon and the pandas case, we didn't really change too much. Or actually, we didn't really change on this panda image to let the let the deep learning classifier to classify that as the gibbon. We only perturb a little from the background. So it's very cost efficient, but still manipulates the deep learning classifier successfully. Any questions, comments? Okay, no. Yeah, so let's move on. Basically, we assume the purifier or the defender is the diffusion model. So we actually just use the diffusion model's very simplified way to present it, and we substitute the original input of the diffusion model with this adversarial example as we presented before. So our goal is to find, okay, so before we see this one, so our previous goal is actually to find the difference between the purified data and the adversarial example and try to minimize this difference bound as much as possible. But at the end, we failed. The reason is solving this diffusion model is very complicated, and basically, we checked with the statisticians and some mathematicians from Oxford, and they're experts on SDEs, but unfortunately, they still cannot really find a good way to explicitly solve it and to derive this bound. So at the end, we use a different way to see the purification results, which is also consistent with the previous idea, is that we project our purified data on the direction of the signal to see how much they are similar. So the similarity increases, it means the purification result becomes really successful, and the true semantic label will be correctly predicted in the downstream case. Yeah. So after some derivation, we found that the bound of this similarity is also controlled by the level of noises, so as empirically discovered in DeepQ before, and also, of course, the signal itself. So basically, we can see a little from this case that the noise level can't be too large. Otherwise, the difference between the purified data and the signal will be very large as well. And the noise can't be too small. Otherwise, the adversarial attack won't be sufficiently diffused or removed. And finally, the classification won't be correct. Yeah. Any questions, comments? No? Okay. Yeah. So this is one case. And second case is to find how can we enhance the purification result. So following the previous idea as well, here we consider the guidance to change the distribution and to find the purified data with higher fidelity and also more rich semantic information to make a downstream classification successful. So here we actually searched for lots of losses because this is how guidance works. The losses, as the guided diffusion model said, it's very important to keep the semantic information. So we first found the MSC loss. Unfortunately, it's already used. And then we searched around. And finally, we found, oh, maybe contrasted loss might be helpful because here, in contrastive losses, we are enhancing the signal for the same image from the last step to the next step in the reverse process. So basically here we keep the semantic information. And also we try to enlarge the difference between one image and the other images, or one image and possibly images from the other clusters or classes, to try to enhance this image's own semantic information. So at the end, this is possibly the one we think probably works. So from this kind of intuition, we did some theoretical derivation to find if it's really the case theoretically. So in this case, we separate the contrastive loss or contrastive guidance into two parts. So the first part, we mainly consider the positive pairs, which means one image's previous steps value and next steps value. So in this case, we are really lucky to find the direction of the signal is what the positive pair represents. So basically, it's enhancing the image's own signal, which means the semantic information will be enhanced. So next step, we move on to the part with only negative pair. So negative pair means this image and the other images in the same step in the reverse process for diffusion model. So here, we're also very lucky that you find it's just the opposite way of the signal. So basically means for negative pairs, is going in the direction of the opposite way, but because there's a minus sign, sorry if you can see that clearly here, because this is a minus sign, so it means reverse the direction of the signal, which means also enhancing the signal. So at the end, theoretically, we prove that for contrastive loss, it can enhance the signal, which means enhancing the true semantic label information in the data, so at the end, to enhance the deep learning classifiers classification accuracy given adversarial examples. Any questions, comments? Okay. Yeah, so building on all the past findings in the theoretical analysis and the theoretical insights, we propose the contrastive diffusion model, contrastive guided diffusion model for adversarial purification. In short, contrastive depure. So in this case, the forward process will follow the previous designs that we still add on the noise to the noise level where we can still keep the semantic information but diffuse the adversarial examples, adversarial attacks as much as possible. So one thing we should keep in mind that do not add too much Gaussian noise to make the whole data to be the Gaussian noise. Otherwise, for the reverse process, we may not to find the data following the same semantic label for the downstream classification. Yeah, and for the reverse process, things will be slightly different because here we add on the contrastive guidance, so we have positive pairs and negative pairs. So same as the theoretical analysis, we want to keep the positive pairs as the same image, but they're just different in the time steps for the diffusion model's reverse process. So basically, it means for one example, for myself, me at this moment will be the same as the next moment as a substance as myself. And for negative pairs, it means on the same time step for the diffusion model's reverse process, this image has to be different from the other ones. So basically, that means we want to separate different semantic information as much as possible. So in a downstream classification, they are easily classified correctly for the classifier. So in a metaphor way, it means that for myself at this moment, I want to be more distinguished and as distinguished as possible from the other ones. So basically, I can still keep myself as myself. Any questions here? No? Okay. Yeah. So basically, for the design of the reverse process, things can be slightly different from what we did in the theoretical analysis because for contrastive losses, we have lots of options for the losses. One is called informal NCE loss. This one is just following what we did previously, that we want to be the same as we are as past, but we want to be different as all the other images in the same time step. But this is going to be very tricky because here we either rely on very small batch size or we have to rely on very powerful computational resources. So basically, there are some requirements. And the second one becomes more sophisticated, called hard negative mining. So this loss is slightly different. It actually builds one distribution for us to sample the negative pairs from this distribution. And this distribution is actually computed from the data given in all this batch, but sampled from them. So it's really helpful to reduce the computational cost and also give very good results at the end. So basically, all the experimental results I'm going to present later is based on this hard negative mining loss. Yeah. So this is basically the pseudocode for our algorithm design. So it's just the same as we did previously, or we discussed previously. But one thing I want to highlight is that here we still rely on solving this diffusion models SDE, like solving the reverse process. So basically here is very computational costly because we had to optimize this T during this SDE solving process, and we had to solve multiple steps. This multiple means at least 100 for CIFAR10 datasets value. So imagine when we are solving for ImageNet, it can be how computational costly it is. So any questions here? No? Okay. Yeah, so if you can see that clearly, so this is the experimental results. We selected a little for CIFAR10, but you're welcome to check the ImageNet results for our paper. Just for a really brief glance, that for CIFAR10, auto attack is currently the very powerful adversarial attack for adversarial purification and also for adversarial training together. So in this case, we outperform the past methods, even including the adversarial training, which are actually trained on this adversarial attacks. So we can still beat them in the robust accuracy, which is quite impressive. And we even beat the pure methods we discussed before by 10% around for the robust accuracy, which is a very high increase. So for the same auto attack, but we changed the adversarial attacks budget a little, we can still beat them, even for the adversarial training methods, which already see these adversarial attacks in their training process. Yeah, so for just a highlight, compared with adversarial training methods, we can also see the same performance result that we perform them for a lot, around 10% for the robust accuracy. Yeah, so there are some key takeaway informations. The first one is that the T star, like the noise level, they can't be too large or too small. So we can keep the semantic information, but still diffuse away this adversarial attack as much as possible. And second is that contrasted guidance, they can enhance the adversarial purification for diffusion models, which is very informative finding. But the other findings are also very interesting. First is that adversarial purification, well, is canon, like diffusion models for adversarial purification, has its impact and also proposed only 3 years ago. So this area is still a very new to explore, and also there are some low-hanging fruits as well. So you're welcome to join this community and discuss and also contribute. The second is that diffusion models for adversarial purification, they actually demonstrate significant improvement against the adversarial examples for classification. So basically, means this track is still workable. And third is that basically the adversarial purification's performance, as we see from this family tree, is really dependent on the powerfulness of the generative model. So as long as we have more powerful generative model, then we can assume the performance can be increased. So we have still 3 minutes, so let me quickly go through a very interesting finding we recently have. That means this is what we emphasized before, that semantic information matters for adversarial purification. So that means basically in the past methods, as we all went through in the previous 27 minutes, they are all unimodal models. So basically that means even when we just keep on emphasizing semantic information is very important, we still have no explicit semantic information given to this generative model to enhance its performance and to really have the clear information on what this semantic information means. Yeah, so based on this gap and based on these findings, we move on a little for a very interesting model setting is that maybe learning the semantic information explicitly by the prompt learning will be really helpful. So we tried lots of methods where we can predict the label from the prompt learning, and also we can maybe do the class agnostic way to remove this label, but still use this explicitly learned prompt or semantic information to enhance our purification. And at the end, we recognize this class agnostic way will be very helpful. So in the prompt learning, we still rely on the clean images. So basically want to avoid this adversarial training setting to maybe limited on the scene attacks. So we still want to benefit from the high generative power. So here we learn the class agnostic prompts based on minimizing the diffusion loss as we did before. But here the diffusion model becomes a stable diffusion model. So we can include this semantic information explicitly and much as possible. So at the end, we learn this class agnostic prompt for the downstream adversarial purification. So here we benefit from this adversarial, this class agnostic prompt like before. Given adversarial image, we use this stable diffusion model to denoise the adversarial images, adversarial noise. So basically, this is also kind of different from the past. In the past, we had to solve this SD in the reverse process. But in our current attempt, we aim to directly solve for this purification or diffusion loss to directly optimize for this purified data, which only requires a few steps. So here, we generated this purified data x0 star. And in the downstream case, it's the same. They want to put them into the deep learning classifier and predict the results. Yeah. So this is the preliminary findings that we basically can see we have some improvement on the adaptive attacks. Adaptive attacks means the attacker has the full information for the whole defender, which means that they can also attack the vulnerability we have in the defender. But at the end, we can still have very good performance compared with the past generative model-based adversarial purification methods. But compared with the adversarial training-based methods, we can still have some gap, and here is also what we are currently working on. Yeah, so just a quick summary is that explicit semantic information really helps for generative model-based adversarial purification. We can also speed up the diffusion models for adversarial purification based on only minimizing the diffusion loss. There are some other findings that probably multimodality will be really helpful as well. So the prompt maybe can be designed in other interesting forms, such as maybe audios or some more modalities. And there's other findings that in the past, people speed up the adversarial purification based on diffusion models on the knowledge distillation. So that requires also a lot on the previous training or distillation process. But here, we directly solve that without knowledge distillation, only relying on the optimization for the diffusion loss. So that's it. Thanks for your time. Any questions are welcome.
Question?
Thank you for the talk. I have a simple question. Can you use diffusion model or this line of research to easily detect there is some attacked input from certain client?
Yeah, this is very interesting, and I think probably we can't. The reason is that the difference at the end, well, this is only my preliminary idea at this stage. The difference between the adversarial example and the purified data in the L2 norms form, like Euclidean distance, will actually be too large.
So I mean, not a single one, but a batch of input given submitted to the cloud service by a client. Then I think because using some smart hypothesis testing method, you can detect that the adversarial, you can know that the adversarial images and the clean images, they come from different distribution.
Yeah.
And because you can purify them, and then some classifier, even without a classifier training, adversarial training can correctly classify the image. So I think the data distribution of the purified image is closer to the clean image, right?
Yeah.
Then, I mean, if you first run some adversarial purification method, obtain the purified image, and you run similar hypothesis testing method like using MMD test, and then you can know that this client submit a lot of a significant ratio of attacked images.
Yeah, I think.
And then you can ban them. You don't provide any service to them because they are problematic.
True.
Yeah. Otherwise, I want to know what's the future of adversarial robustness. Now it's like you already obtain acceptable performance. And later, if you want to further improve the adversarial accuracy or adversarial robustness, it's not necessarily true that you suffer or you sacrifice the natural generalization, but you will suffer from higher and higher computational cost. And the client who are honest, who don't submit any adversarial image, they still consume the same amount of your GPU time, but the one who submitted a lot of adversarial image, they may consume more, right?
Exactly.
If you know this client don't submit adversarial attacked image, maybe you don't need to really run the purification for them.
Yeah.
Of course, it's not forever. You need to randomly check to get some like a quality control. But then, if you don't, if you choose to don't run purification always for the honest client, and for the dishonest client, you always run purification for every input submitted by them. It's unfair to the honest clients.
Yeah, exactly. I remember there's one paper published in ICCV 2024 or 2025. So this is called DiffGuard. So it means they use the diffusion models to guard the downstream tasks where they do the OOD detection. So this is also probably the other way to identify adversarial examples using diffusion models.
Okay.
Yeah.
I just wonder if you can successfully identify which client is honest, which client is not honest, what is the next step?
Purify adversarial examples given by adversarial clients and keep the clean ones for downstream tasks.
But then from the resource allocation perspective, it's unfair to honest clients. Because they are honest, they submit a clean image, and then they pay for the same. Maybe they use very little of the computational resource of the provider.
Yeah,
right?
That's true. Maybe in the later time we can submit some voucher to those clients.
Okay.
Thank you.
So we have already run out of time. So
yeah, sure.
Okay, let's thank the speaker again. Yeah.
Thank you for the introduction. I'm Shinji, belonging to the University of Tokyo and RIKEN-AIP. This talk is based on this paper published in Corto 2024, and the topic is about online learning theory and bandit algorithms. And today's topic is related to these three papers. And first, I'd like to start with introduction of online gradient descent and AdGrad as the background of our research. Online linear optimization or online convex optimization is one of the most basic problem setup in online learning, in which the learner chooses action xt and then observes a loss vector or a gradient gt. And this procedure sequentially continues in t rounds. And after that, performance of the learner is measured by the regret, defined as a difference between the learner's performance, which is a cumulative loss, and the performance of the best fixed solution. So there are many reasons why we focus on the regret. First of all, the regret can be interpreted as a natural performance metric in sequential decision making, including online portfolio selection and multi-unbounded problems. And in the special case of the stochastic optimization setting, in which GT is a stochastic subgradient of some convex function, the small regret implies a small optimization error. I mean, if we get online learning algorithm with smaller regret, then we can get a good stochastic optimization method. And this concept of regret makes sense even in non-stochastic environment. So the regret is considered as a standard performance metric in the context of online learning. And online gradient descent is one of the most basic algorithms for this problem setting. Here we assume that X is a convex and compact set with a bounded diameter, which is at most capital D, and the gradient norm is bounded by capital G. And in online gradient descent, XT is updated in the opposite direction of the gradient with step size eta. And if it goes outside of the feasible region, it brings it back to the region to make it feasible. So this is quite a simpler algorithm, and this achieves a regret upper bound, returns this. So this upper bound is bound depending on the learning rate parameter eta. So here we wonder how to choose the learning rate. So if the most typical choice is to choose this one. This minimizes right-hand side of this. So if we consider minimizing this value, the optimal eta would be this one, and we get square root upper bound, right? But there is a better way. One ideal choice is to minimize this one. If we consider minimizing this, the optimal eta would be this one. Then we can get better upper bound. This is better, especially when the gradient has smaller norm than capital Z upper bound. But unfortunately, this is impossible to implement because we don't know the value of the normal GT in advance. So, but there is some solutions to this issue of impossibility of implementation. It is known as, maybe you are familiar with this. The solution is the Adversarial method. First of all, online gradient descent can be generalized to the method with time-varying learning rate. In that case, the gradient, the regret upper bound is generalized in this form. And when we use this learning rate, which is here, this is sum up to small t, not t. So this can be computable from the observation so far. And with this eta t, we can get GT dependent upper bound. like this. Do you have any questions so far? So this upper bound is quite non-trivial, but it's not very difficult to show.
And this eta is not the order, but the exact value.
Yeah, but that's not the. Yes, but if the constant difference of constant factor doesn't matter.
D is a kind of unknown constant.
In this setting, we consider that capital D is a known value. D is
something large.
Something. In this talk, we assume that the feasible region is given in advance. That means capital D is known. Don't you like?
When we want to set eta T properly, so maybe D is somewhat unknown. Of course, if D is large enough, it's safe. But in practice, we want to make it as small as possible.
Yes.
Not known. So then, essentially, the exact D value of eta T is a kind of proportional number.
Yes, I agree that in some setup, the relation should be assumed to be unknown, but in our main focus, such as bandit algorithms, the feasible relation is, for example, just a probability simplex. So in that case, the region is given in the advance, and we can assume D is known in. So
and that is enough.
It depends.
D is a probability simplex.
Depends on.
It's quite big, right?
Yeah. So it depends on the applications.
I see.
Yeah. So that's a very good point. But in this talk, we assume that the feasible region is given in it. Thank you for the question.
Is that greater than a random variable or is fixed? For GT. Is it a random variable or is fixed?
And it depends, but basically we consider GT is not a random variable. Okay. But we consider the special case of a stochastic gradient setting. GT should be the random variable, and we usually consider the expectation or
so once x1, the initial solution is determined, then the output xt is also determined. It's deterministic, right? It's not a random.
Xta is assumed to be deterministic in this talk. Okay, that's a great point. Yeah. Yeah, in the following, we may consider the setting in which GT is a random variable, but basically we omit the expectation notation to make it simpler. Here, any other questions so far? So I omit the detailed proof, but I'd like to mention the key inequality in the proof of this one. That is, given under this condition, each term regarding the gradient norm is bounded by the difference between the inverse of learning rate. So with this one, the sum of this is bounded by the 1 over eta t by applying the telescoping sum. Then we can get this GT dependent upper bound. So this is a nice technique in the context of online gradient descent. So let's move on to FTRL. FTRL is a generic framework in online learning in which we choose the output by solving the optimization problem, including the cumulative loss for far combined with learning regularizer function. And this is a generalization of the gradient descent. In fact, if psi regularizer is a squared norm, then this rule leads to lazy gradient descent. And another important example is exponential rate. If x is probably simplex and psi is negative entropy, then this update will leads to this one. And this is very well used in the context of many other online learning problems, including prediction with expert advice and other bandit problems. And similarly to the gradient descent, the upper bound for regret upper bound for FTRL can be well analyzed, and the upper bound is decomposed into stability terms and penalty terms. Here, ZT and HT are parameters that depends on the problem setting and the definition of G hat and regularizer function. Here, this table shows some examples of ZT and HT. Here, again, we wonder how to tune the learning rate. Similarly to the case of online gradient descent, we can consider other grad type update rule. In that case, we can get regret upper bound depending on ZT. Here, the upper bound is adaptive to ZT, but we wonder if can we make it adaptive with respect to HT, not only on ZT, but also on the HT. This is a main research question of this study. Any questions so far? So let me move on to our main contribution. Moving on to our approach, I'd like to mention the key conditions of ADGRAD. In the analysis of ADGRAD, the important condition is that each term regarding the gradient norm is bounded by the difference between inverse of learning rates. And even in the analysis of FTRL, the analysis of ADGRAD type update rule, we can interpret this as some essential condition behind this ADGRAD type learning rate. In fact, we can consider this as a starting point of the design of this type of learning rate. So given this, one natural way to generalize this to make it adaptive to HT would be replace H bar with HT. I think this is a quite natural approach. Yeah. And we can, here the left-hand side is corresponding to the stability term and right-hand side is penalty term. So we refer to this approach as stability penalty matching. Just matches the values of stability and penalty. So what we can get from this? This is a main theorem of this study. Given under the update rule explained before, we have this regret upper bound. here we direct stress that this learning rate can be computed in a recursive manner. That is, we can compute eta t, and it's easy to implement. And the first upper bound implies that the upper bound is adaptive, dependent on ZT and both ZT and HT. And the second upper bound means that this also enjoys an Addergrad type upper bound. So you may wonder what is the benefit of being adaptive to HT. Here we can say that this is useful in the design of best of both worlds bandit algorithms. Let me introduce what is best of both worlds algorithm. In the context of online learning or bandit problems, there are two different settings regarding environment have been considered. One is stochastic environment, in which the loss follows a fixed unknown distribution IID. And in adversarial environment, such stochastic assumption, there is no stochastic assumption, but the loss can be arbitrary sequences. And it is known that the algorithms designed for each environment works better. Typically, for example, UCB algorithm performs very well in stochastic environment, achieving log-T regret, but it is poor in adversarial environment. But if adversarial algorithm for adversarial environment like EXP3 works well in adversarial environment, but it's not the best choice in stochastic environments. So we can say that it is important to choose the right algorithm that matches the type of environment. But in practice, it's difficult to choose the right algorithm as the type of environment is usually unknown. So to handle such issue, the best of both worlds algorithm have been considered that achieves near optimal performance in both environments. And our new learning rate is useful in the design of best of both worlds algorithm, in which we determine the action selection probability xt using the FTRL and stability penalty matching. Here, we use a Salis entropy regularizer. And alpha is a parameter between 0 and 1. And as we have seen, by applying the stability penalty matching, we have two different types of upper bound. One is, the first one is dependent on ZT and HT. And the other one is depending on ZT. That's the same as Addergrad type upper bound. Then in the case of bandit problems, ZT and HT is bounded by as this. Here, C alpha is a constant depending on the problem setting and the design of a gradient estimator. So by combining these two inequality, we get two different upper bounds. And the first one implies a log-T regret in stochastic environment, and the second one implies square root T in the worst case. The second one is clear from this expression, and the first one would be non-trivial, but it's easy to show. in fact, in stochastic environment with a suboptimality gap, I mean, if we consider the environment in which choosing the suboptimal gap, a suboptimal action result in the delta mean power round regret, then regret is at least, here XTI is a probability of choosing action I in round T. So the regret is at least this one from the assumption. So we can see that from this lower bound, the sum of 1 minus XTI star is bounded from above by regret again. Yeah, regret is bounded by the expression including regret again. So by solving RT in solving this inequality with respect to RT, we get log T upper bound. Is this clear? Yes. So by this algorithm design and analysis, we get best of both worlds upper bound for many different problem setup. I'd like to stress that.
Implementable?
Yeah. Yes. This is.
Eta t can be determined frequently.
Yeah, eta t can be determined from determined by the observation so far. More precisely, eta t in SPM, eta t is defined so that this condition holds. So eta t can be computed in recursive manner as this. And ZT and HT can be computed at the round of T. So we can compute ET in each round.
Thank you.
Thank you. So I'd like to mention that in conventional study, algorithms are designed for each problem separately. But in this, our method enables us to design our method provide a unified methodology for designing best of both worlds algorithms that can be applied to various different type of bandit problems. Yes, to summarize, the main research question is how to tune the learning rate to minimize this. And our solution is simply choose eta t so that the value of stability and penalty matches. And our main contribution is that by applying this update rule, we get adaptive upper bound. And from this, we get this leads to unified and generic methodologies for designing best of both worlds bandit algorithms. And our paper includes other technical contribution like the discussion regarding the SPM stability penalty matching update rule based on the framework of competitive analysis, but I skipped today. And there are many other future directions, including application to other problems and extension to multidimensional settings. So I think I have already consumed the time, so I'd like to finish. Thank you.
I have a question. So I'm I want to ask about the choice of the regularizer. So then, is it xi alpha, the minimize, is it the non-convex function?
Regularizer is convex.
It's convex. So
yes,
it penalized to become 0. Am I right?
Yeah.
So
it's penalized closing
0.
Yeah.
So then it can be locally convex, strongly convex. So if
it's strongly convex.
If xi is non-zero, it becomes strongly convex.
Yes.
But if xi is 0, so it should go to 0 against this penalty.
Yes.
Then you get like something like a best of both worlds.
Yes.
So, okay, so is this regularization at best of both worlds can be achieved for like a non-sparse optimal solutions? Or sparsity is not so important? I mean,
in general, it's a great point.
Well,
you mean
my point is that like a multi-armed bandit problem is just you select just one arm. It looks like a sparse solution. So yeah, how it is related to your choice of the Taris entropy. Yeah.
In my understanding, the sparsity of XT is not it doesn't matter because.
Okay.
But maybe.
Why you need to care about the 0?
The reason why we care about case x close to 0 is that the reason comes from the definition of the gradient estimator. For example, in the case of multi-armed bandit, the gradient estimator is written as this. So this expression implies that the variance of the gradient estimator become bigger when the value is close to 0.
Okay,
the x is close to 0. So
okay, so that the particular choice of the psi is coming from the design or the kind of loss.
Yeah.
So some structural loss.
Yes.
I see. Thank you. So, other question? No? So then let's thank the speaker again.
Thank you.
Ryuji Hamamoto, I'm the team director of the AI medical engineering team in RIKEN-AIP. So today's my topic of the presentation is AI in healthcare from bench to bedside opportunity and challenges. My team is mainly focusing on the medical artificial intelligence. In particular, we plan to apply the AI technology for clinical settings. So if you have any question, please let me know. Firstly, briefly explain about my academic career. I started the cancer research in the University of Tokyo, Institute of the Science of Tokyo and the Department of Medicine. And from 2006 to 2007, I studied genomic medicine in University of Cambridge. And once returned to the University of Tokyo, and since 2012, I moved to the University of Chicago. And also, I continued to study the cancer research. But as you may know, Chicago is a very famous of the radiology field and one of the centers of the medical artificial intelligence in the United States. So I'm very interested in the medical artificial intelligence and to combine the medical research. And I returned to the Japan in 2016, I became the division chief of National Cancer Center Japan. And I also became the professor of the Tokyo Medical and Dental University. Now changed to the name and the Institute of Science. And since 2017, I became the team leader and team director, and I actively conducted medical artificial intelligence. I'm sorry, my repetition, but I focusing on the clinical application. So, as you know, the RIKEN-AIP Center is one of the Japan's largest artificial intelligence research centers where world-leading, innovative, foundational artificial intelligence technologies are developed. And the National Cancer Center Japan is Japan's largest cancer research center and the central institution for cancer control in Japan. The volume and the quality of its cancer-related information and data among the world's highest standard. So our mission is adaptive and the synergistic cooperation between the AIP and also the National Cancer Center Japan to analyze the volume and the quality of the world-class cancer-related data accumulated in the National Cancer Center Japan using cutting-edge technology from the RIKEN-AIP and apply it to cancer diagnosis and treatment. So National Cancer Center possesses a huge amount of the medically relevant to cancer, including clinical information, omics information, medical images, and PDX model, and pathology report, and radio report. Once we constructed the NCC integrated cancer medical information database and using AI technology, machine learning technologies, we actually develop a new cancer diagnostic systems, a new drug design system, and a support system for personal-based. And we also promoting the movement from RNA to industrialization. Since 2018, the Cabinet Office Government Japan project like the PRISM and the Bridge was added in our project. Our research, between the research and in RIKEN and the National Cancer Center Japan, we already has several social implementation, clinical application, including the endoscopy diagnosis system and also the AI development support platform, or I don't know, to precisely extract the suspected glioma areas from MRI, and also the ultrasound AI system. So first, we'd like to explain about the development of real-time endoscopic diagnosis support system using artificial intelligence to prevent oversight in colonoscopy. Since neoplastic colorectal polyps precancerous region, detecting and removing them during a colonoscopy can inhibit their progression to colorectal cancers. Physicians detect polyps by macroscopic observation, but their polyps are easy to overlook if they are small or their shape is not clearly defined. So to address this issue, we developed the real-time endoscopy diagnostic support systems using artificial intelligence. This is the overview of our systems using algorithms for morphological detection of the region using deep learning, artificial intelligence, and also we use the high-speed processing algorithm and the GPU. The important point is the real-time feedback. So unfortunately, surprise-rate number of regions are missed. For example, based on the physician's technique, also the missing rate is different from the 70 to 48%. Based on the disparities in physicians' skills, you can easily imagine that the physician's techniques are different, which significantly affect the QOL of the patient. That's the reason we like to standardize the medicine using this kind of the medical artificial intelligence. So this is the different algorithm we use. The input is this kind of the endoscopy image and the conversion layer and the pooling layer and the fully connected layer. This is the output. So we use approximately 12,000 regions and approximately 250,000 images for training. This is a real-time video images, the 25 with the protruded regions, and artificial intelligence quickly identifies the region and around. Also, this is a 50 millimeter early stage colorectal cancer, the PSN. And this is a 5 millimeter protruded region. sorry, maybe you don't have enough knowledge for medicine, but this is important result, and also similar the superficial region, and also the similar the superficial region, the 0 to C, and also the 40 millimeter superficial region, lateral throat tumor, LST. So just as I mentioned, our aim is anyway, we applied our findings for clinical settings. That's the reason we conducted the performance evaluation clinical study called the Design AY01 study. So in this case, the verification hypothesis is that this AI system detects colorectal precancerous region and early colorectal cancer, as well as skilled colonoscopist. We conducted AI performance evaluation test clinical study, and also as an attached test, we conduct the physician reading examination. It took a very, very long way, so applying our result for clinical setting, but finally, we got the approval from the Japanese FDA as a medical device in 2020. And we also got the CE mark in Europe. Our product is currently being marketed by NEC in Japan and Europe. And left monitor is the ordinary monitor, and right monitor is our developed artificial intelligence result conducted by RIKEN and National Cancer Center, Japan. And we also applied this model for tumor detection in Barrett esophagus. This is a device that is artificial intelligence to analyze the endoscope images to detect tumors in Barrett esophagus, and is the first product in the world to conform to the CE mark. This software based on this technology is now clinically available in Europe. And okay, where an image is from the endoscope equipment is displayed on the left side of the screen, and artificial intelligence analyzed. Where tumor is determined to be present as a result of the analysis, a still image displayed in the upper right corner of the screen, and the area predicted by the artificial intelligence described as the heat map in the lower right corner of the screen. So advantage using our systems, AI systems that can detect typical and atypical cases by training for endoscopic images of more than 10,000 early stage colorectal cancer and precancerous regions accumulated at the National Cancer Center Hospital. And this AI system can comprehensively and instantly analyze the entire image projected by the endoscopes. By having the endoscopist and artificial intelligence work in union, the endoscopist is able to be aware of the areas that endoscopist was not aware of, which is expected to improve and enhance the accuracy of diagnosis. Actually, other important point is that this AI system can be connected to the endoscopes from 3 major endoscope manufacturers, vendor neutral. Simply connect your existing endoscope to a terminal and monitor equipped with this software to start using it immediately. Because our research is academia origin, the RIKEN-AIP and National Cancer Center very neutral for in the aspect of the commercialism. So that's the reason our system is vendor neutral. This is also the very important point. And actually, we apply our technology for the pathology diagnosis prediction model. This is the colonoscopy result and detection model and determination of the region location. Then conducted the pathological diagnosis. This is a very, very important point in the clinical settings. For example, negative for neoplasia, dysplasia, or low-grade adenoma, or dysplasia, or high-grade adenoma, or non-invasive carcinomas. The artificial intelligence can discriminate this kind of the pathological conditions. So to prevent mixed differential diagnosis, we developed a characterization model that automatically predicts pathological diagnosis using the revised Vienna classification. This is the worldwide standard of the colorectal cancer classification. Then we also conducted the clinical trial, and important point is the performance of our AI model is as well as a specialist of human physicians, and inference time of the artificial intelligence is 0.01 second. On the contrary, endoscopist took about 2 seconds, which means that this AI system quickly identifies the region and identifies the pathological analysis compared to human physician. And this is TC a result of the visualization of the internal feature of the our image result, which significantly identifies the pathological difference, like a normal hyperplasia or adenoma or carcinoma, adenocarcinoma. Fortunately, we also got the medical device acceptance from the Japanese FDA. In this case, it's a class 3. It's a highly controlled medical device, March 2025, and already on the market. So summary and future prospect of the endoscopy AI project, an AI system that can detect typical cases by training from the endoscopic images of more than 10,000 early-stage colorectal cancer and precancerous region accumulated at the National Cancer Center Hospital. And in cooperation with RIKEN's cutting-edge artificial intelligence technology. And this AI system can be connected to endoscope from the 3 major endoscope manufacturers vendor neutral. And future plans that we will improve the accuracy of the artificial intelligence by having it trained to recognize flat or depressed regions that are difficult for humans to recognize. It also aims to address the corrective diagnosis of colorectal regions and the prediction of lymph node metastasis of the colorectal cancer. And by linking CT images, pathological images, and molecular biological information, and other information, we aim to develop a multimodality real-time endoscopic image diagnosis support system that is more highly useful and will further promote development and research towards realization of the advanced and personalized medicine and remote diagnosis. And next project is development of the AI-based filter cardiac ultrasound screening system. This is mainly conducted by the Dr. Komatsu. He is the vice director of our team. So purpose of this research is we developed fundamental technologies for feature cardiac ultrasound screening systems and the development of the technology to detect abnormality in the feature heart structure and development of a method for displaying the detection results that improves the efficiency of diagnosis. So anyway, we focus on the real-time analysis like this. This is a result of the normal features analyzed by our developed artificial intelligence. And this figure shows that the congenital heart disease tetralogy fellow cases. So the physician can easily understand the result of artificial. In some cases, the issue of the artificial intelligence in using clinical setting is a black box problem that we can't understand why this result is conducted by the artificial intelligence. But in this case, easily understand, physician can easily understand the result. And we also developed the graph chart diagnosis, so improvement in the predictability. The graph chart diagram means that the kernel threads the barcode-like time axis and moves it in the time direction and feeds it to the cascade graph encoder as time series information. The transition of the intermediate feature is then displayed as a graph chart diagram like this. And we also conducted the clinical trials evaluation of AI performance in fetal cardiac ultra screenings. And a little bit surprising, green color shows the physician's the skills. This is AUC. And as you can easily understand that the skills are significantly different based on the experience. And this is the standard, but for patient, I think that a little bit serious issue, but because based on the physician's technique, the quality of medicine is different. That is, we prevent this kind of the discrepancy using medical additional entities. This is a very, very important point of the, our project. And fortunately, we also got the pharmaceutical approval for AI-assisted ultrasound. So RIKEN develops artificial intelligence systems for ultra screening the rapid diagnosis of anomalies enabled. So this is a summary of the ultrasound AI project. Future strategies improve and demonstrate the screening accuracy and expand the scope of the testing by acquiring a large volume of additional future ultrasonic imaging and having AI learn from them, and realize the world's pioneering social implementation of future cardiac ultrasound screening using in various forms, including a partnership with the ultrasound equipment and manufacturers. So future goal is first is a goal is to make it a standard feature of fetal ultrasound screening, which is routinely performed as a prenatal test. And the secondary, the training of examiners and the realization of remote diagnosis through cloud computing will significantly reduce the medical disparities between the regions, and through the development of the perinatal and neonatal care, which suffers from a shortage of the physicians, further safe pregnancies and deliveries will be realized. And this is a final project. The reduction of artificial fibrillation is artificial and remote technology. This project is also the RIKEN, NCC, and Tokyo Medical Dental University Institute of Science, Tokyo. So important point is we can identify the stroke based on our actual intelligence in collaboration with the Shimizu City. So the patient undergoing physical examinations at the Shimizu Medical Association Health Examination Center who wish to participate in the study are asked to undergo a regular 12-lead electrocardiogram examination, and the presence of the hidden atrial fibrillation is predicted from the non-seizure electronic diagnosis using our developed artificial intelligence analysis. So important point is, as a result, we are able to detect the hidden atrial fibrillation in 3 patients which has not been diagnosed before, and start treatment to prevent cerebral inflammation. This is in 2022. And updated cases of the 336 patients for whom analysis had been completed as of the January 2029 were found to have the atrial fibrillation, which were not had not been diagnosed at that time. So, which means that RIKEN's technology can completely support the current medicine. Okay, and also time is not briefly explain about the issues. This is also artificial intelligence also, and generative AI also, and in particular precision oncology. The first is knowledge freshness and generalization. As you know, the knowledge of medicine always updated. That is, we need to run the updated data. So secondary is the safety and hallucination and control. In this case, maybe the lag and HITL, this is human in the loop. The important point is artificial intelligence is a very, very powerful tool, but only artificial intelligence is not enough for diagnosis and treatment of the medicine or any disease, I think. So combination with the RAG and HITL is important. And trial eligibility matching, and this is a little specified word, but electronic health report integration and external validation is data. And the data standardized and interoperability. In this case, the domain shift is one of the serious issues in the artificial in medicine. For example, so if we build the model based on the Natural Cancer Center's data, and we evaluate the model using the data from the Natural Cancer Center, we sometimes get very good results. But the data from other institutes, for example, the University of Tokyo hospital data, significantly decrease the accuracy. This is sometimes happened based on the domain shift. So we need to care about the data standards and bias and fairness, or the privacy and synthetic nature and the regulation, liability and workload. So still we possess a serious issues of this field, but I believe that in the future, the medicine will be significantly improved based on the artificial intelligence technology. Okay, this is an acknowledgement. I would like to my greatest gratitude to all members who participated in this project. Thank you for your attention.
Thank you.
Any question or comment?
Questions? Well, okay, so I have some general questions.
Yeah.
So what is some general reaction from doctors? Like doctors is scared about the AI systems. Maybe AI system can replace them. So what is the reaction from doctors? Positive or negative?
Thank you. Very, very important point. So basically, based on the career, I think that in particular, the specialist, the ordinary, and in some cases, specialists criticize this kind of system. So the older people, but but this is, I think, minor. Over 70% or 80% of the physician is very welcome to use this kind of system. The patient too. So that is, this condition is always changing based on the development of artificial intelligence, I think.
I see.
Thanks for the nice talk.
Yeah.
So because we have many machine learning people here
Yeah.
today, so I'm trying to identify any machine learning technological challenge in your topic.
Thanks.
Can you think of any topics?
Thanks so much. So in this case, for example, so one of the biggest issues of the medical artificial intelligence is the black box issue. So we need to show the identical result analyzed by the machine learning. So machine learning is a very, very powerful tool for example, the identification of the some specific structure. But we need to the result for easily interpretable. So in this case, I use the novel strategies for explainability of the artificial intelligence, explainability of the machine learning's result.
But what do you mean by interpretation or explanation in this case?
Yeah,
we have a prediction model.
Yeah.
If you give some input, we have some definite output, right?
Yeah.
Prediction.
Yeah.
Then what do you mean by interpretation?
Interpretation means that the physician can understand the result. That's also a step of the result. Yeah, which means that
yes, but still this means a lot, right? Like we have machine learning model, and sometimes we say, okay, this part of the model corresponds to this edge or this region or something like that. But maybe this is not the explanation you want to have.
Yeah.
Like in machine learning community, we try to understand the behavior of the model in some way.
Yeah.
So this is quite useful for our kind of research.
Yeah.
But in practical, like clinicians' applications, for example, maybe this is not the target. They really want to know the medical explanation.
Yeah, yeah, exactly. Right? Yeah, you are right. Yeah.
But can it be done by machine learning or?
So this is a very, very important point. In this case, we main and goal of our project is clinical application. That's the reason we focus on the understanding by physicians. So in this case, based on the machine learning, I think. So that's if physician cannot understand the result, which is a little bit serious issue in the as a clinical setting.
Like for example, maybe in the tumor case, the story is a bit simpler to me. Suppose chronoscopy example, for example. So suppose the machine learning said, okay, this region could be a tumor. Then what kind of explanation do you want to have?
This is, for example, the pathological analysis. And for example, there are several different stages of the cancer. For example, the low-grade adenoma dysplasia or high-grade adenoma dysplasia or non-invasive carcinoma. Based on the artificial intelligence.
Okay, in this case, it's more like multi-class classification to me. So you have several candidates of like reasons, pathological diagnosis, and you want to choose the most probable one.
Yeah.
This is supervised learning.
As
long as we have data.
So maybe there's some doctor so expert will give some explanation to the each candidate. So then maybe vision transformer can learn that description from data. So
it's not a simple binary classification of like cancer, non-cancer kind of thing, but even if it's cancer, you want to know what the reason behind.
Your mean is why the artificial intelligence identifies this one. Basically the supervised learning. So
this is possible as long as we have data. I see. I think this kind of discussion is quite important.
I see.
Sometimes there's a big gap between real clinical applications and theoretical machine learning research here.
Yeah, indeed.
So we already ran out of time. So
thanks so much.
Again.